Prepare for an extraordinary cosmic event on the horizon. A giant red giant star at the edge of our galaxy is sending mysterious signals across the universe. Through the James Webb Space Telescope, astronomers have made baffling discoveries about this massive celestial body. Renowned astrophysicist Brian Cox issues a dire warning and raises the question: are we witnessing a catastrophic supernova explosion that could change our night sky forever? Let's get into the details. In the vastness of space, where stars come to life, blossom, and finally meet their end in a brilliant spectacle, one star has recently attracted the attention and concern of astronomers and the public alike. That star is Betelgeuse, a big old red supergiant that sits prominently in the constellation Orion. Although its unique reddish hue and changing brightness have long fascinated observers, recent developments have increased interest in this celestial giant. As we explore the nature of Betelgeuse, we find ourselves on the brink of a potentially monumental event in the life cycle of a star. But what could these changes in Betelgeuse mean? Are we witnessing the prelude to an incredibly spectacular cosmic spectacle? Betelgeuse, approximately 764 times the size of our Sun, is a massive stellar behemoth almost beyond human comprehension. Imagine a star so massive that if it were to replace our Sun, its surface would extend beyond the orbit of Mars and embrace Mercury, Venus, Earth, and Mars in its starry embrace. This remarkable size not only shows the physical characteristics of Betelgeuse, but also highlights this stage in the life cycle of the star. As a red supergiant, Betelgeuse is in the twilight of its existence, characterized by expansion and cooling after a lifetime spent fusing a hydrogen core into helium. Although the current red supergiant stage of Betelgeuse is humanly relatively young, about 8 to 8.5 million years old, it is the result of millions of years of stellar evolution from the hot blue star to the red giant we see today. Betelgeuse's distinctive reddish hue comes from its cooler surface temperature compared to stars like our Sun. While the surface temperature of the Sun is about 5,500 Kelvin, the cooler surface of Betelgeuse registers a temperature of about 3,500 Kelvin, emitting light at wavelengths that give it a red appearance. This color is not only visual, but provides insight into the physical state and processes of the star in its vast gaseous space. Betelgeuse's mystique is enhanced by its historic color change. Ancient Roman and Chinese writings suggest it was a yellowish star about 2,000 years ago, and Arab scholars described it as red in the 8th century. This color change in human history provides valuable clues about the evolutionary path of the star. Betelgeuse's changing glow is just as fascinating. As a semi-regular variable star, its light waxes and wanes periodically after a characteristic light dance after a cycle of 400 days and longer, about 5 years. Sir John Herschel has documented these cycles since 1836, and perhaps even earlier in indigenous oral traditions. But what adds to the mystery of Betelgeuse is not only its changing brightness, but also its irregularity. Unlike many stars that follow a predictable pattern, Betelgeuse sometimes deviates from its rhythmic dimming and brightening, suggesting complex and less understood processes within its massive form. In a recent groundbreaking revelation, Betelgeuse caught the attention of astronomers around the world with a sudden and dramatic change in its appearance, now known as the Great Dim. In late 2019, the red supergiant Betelgeuse, one of the brightest stars in the night sky and a prominent part of the Orion constellation, began to mysteriously dim. The decline of the star was so intense that it began to lose brightness at an average rate of 0.1 magnitude per day and reached its lowest brightness in February 2020. Betelgeuse, normally visible with the naked eye even in light-polluted areas, has significantly decreased. Even amateur observers could detect the change. Tracking Betelgeuse's activity, however, comes with a challenge: the paradox of time. When we look at a star like Betelgeuse, we don't see it as it is in the present, but as it was in the past, because light takes time to travel to us. In the case of Betelgeuse, some 725 light-years away, the light visible today left the star nearly 7 centuries ago. This lag makes it difficult to predict and observe sudden changes in a star's behavior when we are essentially looking at its past. The Betelgeuse dimming event reminded us of the inherent difficulties of real-time astronomical observations and the limitations of our understanding when dealing with vast cosmic scales and the resulting time paradoxes. Andrea Dupree, associate director of the Harvard-Smithsonian Center for Astrophysics, and her team closely watched the unfolding celestial drama using the Hubble Space Telescope. They analyzed the behemoth star as part of a 3-year study to monitor variations in Betelgeuse's outer atmosphere. These observations provided unique insight into the dynamics of a variable star like Betelgeuse, which regularly expands and contracts, causing fluctuations in brightness. Hubble's sensitivity to ultraviolet light allowed scientists to study layers above the star's surface that were partially heated by the star's swirling convection elements. Additional analysis of Hubble spectra taken at various points in 2019 and 2020 helped measure the movement of material in Betelgeuse's outer atmosphere, focusing in particular on the magnesium-2 lines that indicate the atmospheric conditions of the star. These observations showed that material is moving at about 200,000 miles per hour from the surface of the star into its outer atmosphere. This hot, dense material eventually extended millions of kilometers from Betelgeuse and was the precursor to the dust cloud that caused the star to darken. Dupree and his team estimate that approximately twice as much material was lost from Betelgeuse's southern hemisphere during the 3-month eruption. This mass loss was significant, especially considering that Betelgeuse, like all stars, is constantly losing mass, albeit at a much faster rate than our Sun. The scale of this massive explosion and the decrease that followed gave rise to a debate among astronomers as to whether this event could be a precursor to a supernova explosion. The proximity of Betelgeuse, some 725 light-years from Earth, adds to the intrigue, as any such explosion would be visible from Earth and would offer a rare opportunity to observe a supernova up close. However, the question remains, what does this dimming event portend for the future of Betelgeuse? Is this a sign of an approaching supernova, or just a unique episode in the long and complicated life of the star? Several theories have been proposed to explain this sudden change. One prevailing theory proposed a stage in the supernova explosion process that gained traction when Betelgeuse was believed to be nearing the end of its life. Another widely discussed theory suggested that the dust could come from Betelgeuse itself and block our view. Red supergiants such as Betelgeuse can leak material, and it has been suggested that this material can form a dense cloud of dust that causes the dimming effect when viewed from Earth. Another explanation involved changes in the star's photosphere, the visible surface layer, which can affect its apparent brightness. Analysis using different observational methods was used to solve this puzzle.
Spectroscopic studies have shown a decrease in the effective temperature of Betelgeuse, suggesting that the darkening may be caused by a large dark spot on the surface of the star. This theory was supported by the observation that Betelgeuse's temperature decreased by at least 170 kelvins during the dimming, suggesting significant surface changes. Ultimately, the breakthrough in understanding this strange event came from the Hubble Space Telescope, humanity's watchful eye in space. Hubble's observations indicated that the dimming of Betelgeuse was probably due to a significant ejection of hot material into space. This material formed a dust cloud that obscured part of the star's surface and reduced the amount of light reaching us from Betelgeuse. The dust cloud is thought to have formed from superheated plasma escaping from a large convection cell on the star's surface and carrying it across the hot atmosphere into the cooler outer layers. As it cooled, it formed dust grains that created a cloud that obscured light from about a quarter of the star's surface. Hubble's spectroscopic observations of ultraviolet light, which began in January 2019, were crucial in piecing together the timeline leading to Betelgeuse's dimming. Those observations detected evidence of dense, heated material moving through the star's atmosphere in the months before the dimming. In December 2019, several ground-based telescopes observed the decline of the star, especially in its southern hemisphere. Material initially brighter than the star's normal luminosity eventually moved outward and cooled to form a dark cloud. The hypothesis proposed that this outflowing material and the resulting dark cloud caused the star to dim suddenly. The scale of this adjustment was truly monumental, and it thrust Betelgeuse into the astronomical spotlight. The star ejected about 400 billion times more mass than is normally released in a normal coronal mass ejection. This ejecta material, which is thought to weigh several times more than our Moon, was an important event not only for Betelgeuse, but also for advancing our understanding of stellar mechanics. What are the implications of such a massive ejection of material for Betelgeuse and supernova theories in general? The effect is profound and challenges traditional notions that red supergiants spread mass at a constant rate before dying explosively. Instead, the extent of its removal,